All right. Hi. So we'll continue the discussion in 8701 on units. So this unit is on units. Why is this an important discussion? Is because it is very convenient and it simplifies lives quite a bit if one does not use SI units in the discussion of particle physics, decays in particle physics or cross sections. And it's also important to avoid carrying around large exponents. Simply when you have a conversation, you want to talk about things which are, of order of one of things instead of 10 to the minus 28 things. One example is the introduction of a new unit for cross sections, often used for cross sections, which describes an area, and that unit is barn. So we talk about cross sections of barns or femtobarns or picobarns, and one barn is defined as 10 to the minus 28 square meters. Physics processes, the ones at high energies, for example, the ones we discuss at the Large Hadron Collider, are typically of the order of a picobarn, 10 to the minus 12 barns, or one femtobarn, 10 to the minus 15. So there's an interesting story to barns and why this was introduced. The unit came out of the Manhattan Project. The idea of the scientists was to confuse potential spies towards what cross sections for nuclear processes are. And so they introduced this unit of a barn, and they were trying to characterize nuclear collisions, maybe an accelerator shooting something at a target, and one barn is a cross section where it's really, really hard to miss. So it's a big cross section. In this context, also the shed was introduced. This is not very popular today anymore. And it turns out that this idea of confusing the readers of papers or of discussions turned into a new standard. So we talk about those barns and picobarns and femtobarns specifically quite frequently. So this is just one example. This is not really changing the units, but just avoiding carrying around exponents. But we also in particle physics and in nuclear physics use a system called natural units. This system is based on fundamental concepts of quantum mechanics and special relativity. So the idea here is that we replace kilogram, meters, and second by h bar, which is a unit of action in quantum mechanics, c, the speed of light, and GeV, where GeV, a typical GeV is the approximate mass of a proton. So when you do this transformation and then use simplified option of setting h bar and c to 1, you find that energies are expressed in GeV, momentum is expressed in GeV, and mass is expressed in GeV. That means when you talk about relativistic equations, E equal mc square, and all those things, m, e, and also the momentum have the same unit. That simplifies quite a bit. Time has a unit of 1 over GeV, length has a unit of 1 over GeV, and area has a unit of 1 over GeV squared. So that's the simplification. You might think that you lose information by setting fundamental constants to 1, but you actually do not, because you carry with you in your equations the dimension of the problem. If you want to do a quick exercise here, I invite you to calculate the charge radius of a proton, which is 4.1 over GeV or per GeV, and convert this back to SI units. Again, it seems like we lost information here, but just from the dimensional analysis, you can figure out what the answer is. And the hint here is that h bar c is equal to 0.197 GeV femtometers. So you should already know the answer from previous discussions in the lecture, but the calculation is rather straightforward. On top of this, it's useful to use Heaviside Lorentz units and combine them with the natural units we discussed. So what we do in addition here is set the permittivity in free space to 1 and also the permeability in free space to 1, so epsilon naught and mu naught to 1. When you do that, you basically combine or tie the electric charge to the strength of QCD. And so alpha, the strength, the dimensionless fine structure constant, 1 over 137, becomes E squared, the electric charge square over 4 pi. So this is also very convenient to have this kind of convention. So we'll use those natural units as we go to class. In some examples we use SI units, in others we use natural units. This will always be clear from the problem we're looking at.